Shara, have you started recording?
Yes, I have. Thank you.
Okay, great. So it's probably time to get started. Good afternoon, everyone. Welcome to the HAO Colloquium. My name is Stanley. I'm the host for the presentation today. Today, we're very glad to have Dr. Catherine Garcia from the Goddard Space Flight Center of NASA. So Dr. Garcia started her career in heliophysics as an undergraduate at Rice University and followed by a PhD from Boston University, working on atmospheric ion escape with the multi-fluid airflow model, Lion-fed Mobari. And in 2012, she moved to NASA Goddard as a postdoc fellow and has stayed at the Goddard ever since. She's currently a magnetosphere, ionosphere, thermosphere subject matter expert at the Community Coordinated Modeling Center, or CCMC. And she's a deputy project scientist for the GDC mission. And her research interests involve a wide range of high-latitude magnetosphere, ionosphere, thermosphere interactions at Earth, Jupiter, and beyond. Today, she will talk about magnetosphere, ionosphere, thermosphere modeling and the validation at the CCMC. Now let's welcome Dr. Catherine Garcia-Sage. Katie.
Thank you, Don. So as you can see, I've added a subtitle here, preparing for the GDC era. So of course, CCMC, the Community Coordinated Modeling Center, is Community Coordinated Modeling Center. GDC is planned to be a community mission. So I want to acknowledge the many contributions of our community members throughout this talk, and I apologize in advance for any that I miss. But up front, in particular, I want to acknowledge the CCMC ITM team, Jia Yue, Mingyang Chu, Jack Wong, and Josh Pettit. The CCMC Komodo team, Rebecca Ringat, Lutz Rastetter, and Darren Dezu, and of course our director, Masha Kuznetsova. Their contributions can't be contained by any particular reference. They're spread throughout the whole talk. And I will also want to acknowledge upfront Zach Waldron at CU Boulder. I'll be talking extensively about a collaboration that we're working on. And I want to acknowledge Shimoka Matsuo, who's working a lot with CCMC in preparation for the GDC era. And of course, Doug Rowland, the GDC project scientist. So I just wanted to start with saying a little bit about myself, adding a little to the introduction that Don gave. I know I met some of you when I was just a little grad student at Boston University, maybe even before that, when I was an undergrad at Rice. I came up through CISM and was working at the time with the LFN magnetospheric model. I took a little foray into the solar wind, working with Enlil for a bit, came back to the magnetosphere after that, and carried out one of the first implementations of ionospheric outflow into the multi-fluid LFN model. That work sparked my interest in the ionospheric source of escaping plasma. So I moved down in altitude. By this time, I was at NASA Goddard as a postdoc. I worked a bit with fast data, and eventually I started working on the polar wind outflow model, Alex Glosser's model. I adapted this model to Jupiter and exoplanets, and I again grew increasingly curious about the source of the escaping plasma and became interested in the thermospheric source population and thermospheric influences on electrodynamics. And I'm now working at the Community Coordinated Modeling Center. So it's been a meandering path. Probably I could actually depict it a bit more like this. The various research projects and collaborations I'm working with now involve threads of all
nice
of
to
them.
meet you. Nice to meet you. What's from Imo State?
Sorry. To the audience, could you please mute yourself? Thank you. Sorry.
So I hope this talk won't seem too scattered. I wear a lot of different hats. And I recently, a couple of weeks ago, became one of the deputy project scientists for GDC. For this talk, I'll mostly be wearing my CCMC hat. I'll of course be talking about GDC too, but looking at it from more of a CCMC perspective, because looking towards the future, there's a lot of important work that needs to be done that involves both CCMC and GDC needing to be ready with community models to support GDC and related synergistic science, as well as supporting the research to operations pipeline and needing to be ready with data assimilation models so that we'll be able to assimilate GDC data. So that's a summary of where I'm coming from with this talk, tying a bunch of different threads together, but looking primarily from the perspective of CCMC in this case. For those of you who are less familiar with the GDC mission, the Geospace Dynamics constellation is set to launch around the end of the decade. It's planned to be a 6-satellite constellation that will fly at about 400 kilometers through the ionosphere and thermosphere to sample that region at varying temporal and spatial scales. It'll start out in 6 closely clustered high latitude planes. Let's see, I wanted this to start automatically. There we go. And then it will spread out as those planes process at slightly different rates, which will allow GDC to study first local, then regional, and then global scales. And then late in the mission, may start to come back together again as some of these orbits process all the way around with respect to some of the other orbits. So 3 of the instruments have already been chosen, either a Langmuir probe led by Lila Anderson, an ion and neutral mass spectrometer led by Mehdi Benna, and an auroral ion and electron electrostatic analyzer led by Dan Gershman. In addition, there are 2 instruments that are still to be selected. They're in competitive phase A studies right now, but we're counting on the eventual selection of a magnetometer and a thermal plasma instrument, and are also working on sourcing a GPS RO for GDC. And all 6 of these instruments will be identical on the 6 GDC spacecraft. Now, GDC has 2 primary scientific goals. The first goal focuses on high latitude forcing to understand how the high latitude ionosphere thermosphere system responds to variable solar wind and magnetosphere forcing. And the second goal is to understand the internal processes in the global ionosphere thermosphere system and how those internal processes redistribute mass, momentum, and energy. So starting with high latitude drivers, one of the things we want to do at CCMC is to give users more flexibility in specifying the high latitude forcing for ITM models, as well as providing additional high latitude forcing models for comparison. So bringing in new high latitude driver models and new ways of visualizing them. And so we have 3 models that I've highlighted here, super darn convection models, such as Thomas and Shepard 2018, and a few other empirical models derived from super darn high latitude convection data. The AmGeo model, which is an Amy-derived model by Tomoko Matsuo, and the Adelphi model, which is Bob Robinson's new model. It takes Ampere observed field-aligned currents, and from those derives a host of other high-latitude driving parameters like conductance, like Joule heating, energy flux. And so those are our three new models, along with our legacy models, the Weimar convection model and the Ovation Prime auroral precipitation model. So I have those 5 models shown here. On the bottom left, we have the Weimar model. Center is Ovation Prime, and bottom right is the Adelphi model. So those 3 are shown with our standard IDL visualization. So if you've ever been to the CCMC webpage, I'm sure you've seen these visualizations. And so that's what we've used in the past for all of our models. We're beginning to move to a new system called Komodo. So that's shown in the upper right with the AmGeo model. We can see a Komodo visualization of the Pedersen conductance. And Komodo is a open source Python package. It's available on GitHub. And with this package, our goal is to be able to not only visualize all of our models for online visualization the way that we did with the previous IDL visualizations, but also to make these same visualizations available for users to create themselves, to download model data and visualize or analyze each of those models themselves on their own computer if they want to. And so Komodo will make it easy to do the same visualization or analysis for all of these models. And then top left is showing the superdarn convection model. And this is showing the modeler supplied default of the visualization. So along with giving users more options for high latitude drivers to visualize and analyze, we also want to give them multiple options for visualization, both standard CCMC visualizations and modeler supplied visualization options. So we're also offering users more options for high latitude forcing in both GITM and TiGCM. So in GITM, we previously included only the Weimar convection model along with Fuller, Rowell, and Evans precipitation model. We're now expanding that. We've recently added support for Ovation Prime precipitation, as well as the FTA model. This is a brand new model derived from polar UV image data, imager data, not to be confused with image data, as well as one-way coupling with SWMF, so that the SWMF magnetospheric model can be used to drive GITM at high latitudes. For TiGCM, several options are already available, including CMIT, which is the two-way coupled LFM TiGCM model. And starting with TiGCM, we'll also be able to drive the model with assimilated high latitude driver data with the AmGeo model. So we're currently onboarding that for being able to drive TiGCM with AmGeo. So that will be a big step forward. also, as we transition from the LFN magnetosphere model to GAMERA, we're looking forward to offering one-way and even two-way coupling with GAMERA. And so we're interested to hear about different options for TiGCM and WACMX that will be available or will be made available in the future, especially as work from the CGS Drive Center continues and picks up speed. We're really looking forward to seeing those advancements and seeing how we can make those available to the community. So I know there are already a lot of strong connections between CCMC and HAO through Jia and Minyang and Jack. And especially when it comes to high latitude driver options, I'm also interested in working with you there at HAO, as well as the folks out at APL, to improve our offerings for users in this area. Now, one of the things that GDC won't study directly is the solar forcing. So there's no EUV monitor on GDC, but of course, it will directly study the effects of solar forcing. So we want to make sure that our models are going to be able to well represent those effects of solar flux driving. So our new postdoc, Josh Pettit, is actually still living out there in Boulder, just started working for both CCMC and GDC a month or two ago. And he's working on compatibility of our models with FISM2. So he's starting out with WACMX and GITM, and working to offer both daily and flare FISM2 drivers. And we hope that eventually he'll be able to do the same with TiGCM and CTIP-E. So that's an overview of our geomagnetic and solar forcing efforts. So focusing on goal 1 here. Another area that we're working to expand is data assimilation. So that can be used eventually for both assimilating data from GDC when it starts to arrive and in the mission planning stages with OSSIs or observing system simulation experiments. So data assimilation models aren't completely new to the ITM group at CCMC. We have the USU game data assimilation model. It assimilates GPS TEC data and provides the global ionosphere. And so this is a model that Minyang Chu is currently working with, keeping it up to date with all of the GPS TEC data that's available. Now for the GDC era, we'll have even more data that we'll be able to assimilate. And so, we're working on bringing some relevant models to CCMC, namely AMGEO, which will look at the drivers, and DART, which will be used with TiGCM to look at in situ ionosphere and thermosphere data and assimilate that into TiGCM. So this is a bit of an oversimplification probably, but we're planning on AMGEO being able to assimilate data from instruments like CAPE, the auroral ion and electron precipitation instrument, as well as the magnetometer, which will be able to derive currents. And with DART TiGCM, we'll be able to assimilate other data, such as in situ parameters and GPS RO. So we're working on bringing the DART framework over here, working with Jeff Anderson, who's of course there at NCAR, and again, working with Tomoko Matsuo on this, starting with TiGCM and eventually may expand DART to other models. So with these assimilative capabilities, we'll be able to allow CCMC models, allow users to make use of CCMC models, both to prepare for GDC with OSSIes, observing system simulation experiments. So this will simulate how the models will make use of GDC data using simulated GDC data. And then after GDC launches, with observing system experiments. So to demonstrate how these models how the models actually do make use of GDC data down the road. So another way that we're trying to prepare for GDC is with model validation. And the reasons for this are many. For one thing, we want to be aware of what are the current strengths and weaknesses of our models, allowing us to better address GDC science. We also are asking, what needs to happen to move these models along the pathway from research to operations. GDC is planned to not only have science data, but also real-time, very low latency operational data that will be made available to agencies like NOAA, DoD, any other operational partners who may be interested in it. So we want to make sure that our models are also ready for when GDC real-time data starts coming down. And finally, we want to be able to trace improvements in our models, both leading up to GDC and then improvements that we're expecting to result from GDC. And so with validation over time, we'll be able to track those improvements over time. Now, one of the things that we want to look at in particular is thermospheric expansion. Everyone's new favorite event. In February, there was the loss of 40 Starlink satellites because of a geomagnetic storm. If we'd had real-time data from GDC, that would have clearly shown an increase in the orbital drag environment starting about 12 hours ahead of the Starlink launch. Would that have made a difference in what SpaceX decided to do? Who's to say? But at least it's possible that with this in situ data, it would have made a difference. Right now, we have very few direct measurements of the thermosphere. It's a vastly data-starved environment. We haven't had in situ direct measurements with composition since the 1980s. We've had accelerometer measurements since then that you can see on the plot on the right, but still it's not really enough. We're in danger really of overfitting our models to these few measurements that we have. So in order to bring in more data, we have a collaboration between CCMC, Space Weather Trek at CU Boulder, and the Geodyne 2 developers at NASA Goddard. Geodyne is an orbit propagator from the geodynamics group at NASA Goddard. And so in collaboration with Space Weather Trek, especially Zach Waldron, that I mentioned at the beginning of my talk, we now are able to run Geodyne with CCMC-hosted thermospheric models. So Zach Waldron is a research assistant at CU Boulder. He's done an amazing job setting this up on CCMC systems and doing some initial validation work for us. And this setup allows us to use orbital data as a proxy for neutral densities so that we can start to get around this problem of how data starved the thermosphere is, and directly start to validate the effects of neutral drag on satellites. So how are we doing this? We're using precise orbit determination of the ICESat-2 orbit from the Geodyne group. These precise orbit determination, or POD solutions, have an accuracy on the order of centimeters, and that precise orbit is shown schematically here with a black line. The red line shows a modeled orbit calculated from only known physical forces. So let me go a bit more into what the differences between these two orbits are. To determine the POD solution, Geodyne carries out adjustments of the acceleration of the satellite, as well as adjustments of the drag coefficient. And those two adjustments allow Geodyne to better match the observed orbit. The problem is that these adjustments partially compensate for any inaccuracies in the thermospheric model. So when we take out these adjustments and we rely only on forces that we're able to model based on known physics, then the difference between those two orbits is the residual. So the differences between them then point to mismodeled forces, and the most likely mismodeled force is the drag acceleration. So here we're using the residuals as a proxy for inaccuracies in the thermospheric models. So the first thing that we had to do was to update Geodyne to use some of CCMC's thermospheric models. So we added the models that are outlined in orange here. Empirical models shown primarily on the left, physics-based models shown on the right, and HASDEM, which is in a category of its own. HASDEM is an operational model. Its data is simulative, and it's not publicly accessible. So what we had to do is use publicly available output from the HASDEM model, and that's what we're comparing against in the plots that I'll show in a minute. So for the empirical models on the left, these are able to be included directly into Geodyne. For the physics-based models, we're using the Komodo Python package for this. So again, Komodo is able to take in output from physics-based ionosphere thermosphere models, and then analyze it. And we use this capability to fly through the model and use those model outputs in the Geodyne orbit propagator. And then GITM and WAM-IPE, I just wanted to note, we're also adding support of those in our Komodo Geodyne system. So for our initial study, we're again using ICESat-2 data, and this is showing the different densities along the orbit for 6 of the models that we've included. So you can see here that the densities are highest for INSYS 2.0 and TiGCM. They're lowest for DTM 2020 and C2B, and HASDEM and JB 2008 are in the middle. For this initial study, it's a 2-week period during solar minimum, fairly quiet F10.7 flux. There are a couple of events at the beginning and then toward the end where we have some activity in KP. And then this is showing the orbit residuals. So these residuals, like I said, point to point to mismodeled forces in the physics-based setup. And so what we see here is the residuals shown on the top, and then the root mean square error shown on the bottom over this 2-week period. The RMSE is averaged over each day in this case. And you can see from looking at this that the top ones, INSYS 2.0 and TiGCM, those were the ones that were the highest density in the previous slide. Then DTM is DTM and C2B that were lowest density according to the RMSE here, maybe under predicting the densities. And then JB 2008 and HASDEM have the lowest root mean square error. We expect HASDEM to have the lowest error because this is a data assimilative model. So there aren't surprises there. JB 2008 also seems to have some data assimilative type capabilities, I'd say. So some of the inputs can be adjusted after the fact to take into account observed orbits of some of the satellites that are used for HASDEM data assimilation. So, as it turns out, though, the residuals can reflect not only differences in the thermospheric densities, they also can reflect errors in the drag coefficient. So this is a problem because we don't know exactly what the drag coefficient is. So the drag coefficient CD that we have here is an estimated drag coefficient of 2.2. This is what Geodyne is using for ISAT. But if that drag coefficient isn't quite right, then it could bias the results toward over-predicting or under-predicting densities. So in order to account for the fact that we don't know exactly what the CD is, we calculate the optimal CD, the optimal drag coefficient for each of the models. So this is showing that calculation. The best CD for C2B in this case is 4.37. The best CD for IMSIS. Well, I can't actually read that, 1.24. And so if we then apply that optimal CD to each of the models, then we can effectively debias the models. And that allows us to look not so much at whether the model is overall too high or too low, but to look at the fluctuations over this 2-week period and how the model responds to changes in KP and F10.7. So with these adjustments to a common baseline, we can compare these relative responses. So again, on the top, you can see the residuals for each day. They're all much smaller now, and the root mean square error is also smaller. Another thing that stands out is that if you look toward the beginning of the 2-week period and the end of the 2-week period, actually, I'll go to, I'll go to the next slide. So again, the beginning of the 2-week period, the end of the 2-week period, we can look at the adjusted densities and see how these different models respond to the KP, for instance. We can see a very large response to KP in the JB 2008, the orange line that we can see whenever the KP, the black line on top, has a strong fluctuation, you see that same very strong fluctuation in the orange line on the bottom. So JB 2008 here has a strong response to the KP index. DTM 2020, for example, with the red, it starts out along, with the other models, and then falls off in density a bit more than the rest of the models do. So we can see some of these differences. And again, this is based on adjustments using different drag coefficients for each model to debias to a common baseline. So this is, oh, sorry about that. Don't know if you can hear my kids screaming in the other room. This is the CD adjustment, sort of all 4 panels that I just showed on the same slide so that you can compare. The RMSE tends to be higher for these models at times when there's a higher KP. And then for most of the models, it's lower in the center where you have quieter KP. And then this is just going back to one of the points I made before about wanting to track the model performance over time. When we first started working with Geodyne, it was a little bit of a time capsule. The geodynamics group doesn't have thermospheric models as their top priority. So the models that they had in there initially were from the 70s and 80s, Jakia 71, DTM 87, INSIS 86. So one of the first things that Zach did was update each of these models. And so this is showing on the top the orbit densities for the original models compared to the updated models. So for example, Jakia 71 is shown on the top left in gray, and then in orange you can see JB 2008, which is the updated version for DTM comparing to DTM 2020, and then INSYS 86 and INSYS 2000 compared to INSYS 2.0. So for all of these models, the updated models have lower densities for the ICESat orbit. Also looking at the root mean square error, you can see by comparing the original gray lines to the more colorful updated models, there's a pretty big decrease in the root mean square error for each of these. So it's really interesting to see these significant advances across the board in all of the empirical models over the past decades. And it would be great to be able to do the same thing with physics-based models to track those changes over time and see how they improve. So to summarize our validation work, we have a new tool and new data for the assessment of modeled thermospheric densities. This assessment directly relates to operational goals, predicting neutral drag effects on satellites, rather than assessing the densities directly. And we've carried out an initial 2-week solar minimum study. We have a lot of plans for extending this, foremost to include a physics-based drag coefficient model in Geodyne. So that will help to get rid of that uncertainty in the drag coefficient so that we can be more confident in the drag coefficient to know that we're not biasing our results toward favoring over predictions or under predictions of density. Again, we're going to add support for GITM and WAM-IPE. We're going to expand the time period that we look at, as well as expanding to new satellites. I also want to point out that we have the potential to use CCMC-hosted neutral density models in planning future heliophysics missions to LEO with the Geodyne orbit propagator. So in summary, we're expanding our high latitude models and forcing of ITM models. We're improving our solar forcing of ITM models. We're bringing on data assimilation capabilities for OSSIes in preparation for missions like GDC, as well as for research to operations and showing what needs to be done to make these models operational. And we're carrying out satellite drag model validation. Finally, I want to mention that all of this is actually just a slice of what CCMC is doing in the ITM area and even in preparation for GDC. I haven't had time to mention most of the extensive work that Jia Yue, Minyoung Chu, and Jack Wong are leading in this area at CCMC. Things like TEC model validation, neutral density validation, and ionosphere, thermosphere driving from below. All of these also very relevant to preparing GDC, preparing CCMC for GDC. So I want to mention that there's more. And I welcome any questions you have, as well as, like I said throughout my talk, any ideas or any collaborations for what we can do to help prepare our community with models that are ready for the GDC era that's coming up. Thank you.
Okay, thank you, Katie. Yeah, it's really exciting to learn the updates about the GDC mission and how CCMC has been prepared to support the emerging mission. So now it's question time. Anyone, please? Okay, I think people are still thinking about the questions. I do have a quick one. So in the earlier of your talk, you mentioned different options as the highlighted driver. This may be a question for the community as well. So how do we reconcile like when the different models have the discrepancies?
That's a really good question. No, one of the things that we need to do is to expand our validation. So right now, what I showed, for example, in the satellite drag validation was just using all of the default driving options for all of these models. But another of the things we can do is, for example, drive TiGCM with all of the different driving options and to compare how it responds using different drivers. So that is a really, I think, important way that we can move forward and start to look, because each of these models is going to have different strengths and weaknesses, different times when it might be able to respond better or might not be able to predict the environment as well. So we really need to be able to do a broad validation across different parameters and across wide time periods to find out what those strengths are and where improvements may be needed.
Yeah, I see. Yeah, thank you for that. I think I agree it's really important, not just for data model comparison, but also the cross-model comparison and validation is also very important. Okay, let's go around the room again. Please take the chance. Kate is the deputy project scientist of the GDC mission. So if you have specific questions regarding the mission, it's also a good time to ask her directly. Okay, our audience is a bit shy today. Well, I do have a lot of questions, but I really want to reserve the opportunities for the audience. But okay, if people want me to ask it. Yeah, since one of the important topics about the satellite drag, and you also emphasize the importance of direct measurements. So first, could you confirm whether GDC can directly measure the neutral density, for example, or not? Yes?
Yes. Yeah,
Okay.
GDC will be able to directly measure not only neutral density, but also composition with the MOSAIC instrument. Okay,
that's great. I know traditionally, like with swarm data or other satellite, we have to infer that based on the accelerometer measurements. So yeah, that's really good to know. So yeah, you also mentioned, sorry, I'm still asking. You also mentioned a few instruments. That's the two instruments in phase one, and one another to be determined. So, well, if you're comfortable to share, do you have any idea about the timeline when the outcomes will come up? No. Okay.
I'm not sure. That's
okay.
That's up to headquarters.
Right. Okay, I see. Yeah, I know in the community, people are trying to show their support, like by reflecting their voice in some white paper. So yeah, we do wish this mission can get launched soon. Okay, I saw a question from the chat from Sui. Thanks for the talk, Catherine. What is the planned GDC altitude for now?
It's planned to be at 350 to 400 kilometers.
Yeah, that's very close to like Swan, right? Okay, I see. Others? Lee, yeah, please. unmute.
Yeah, I just want to clarify, is the neutral density, because earlier we were talking about the neutral density, is that the neutral number density, not the neutral mass density, right?
So it's using a mass spectrometer, so it will be able to differentiate the different neutral compositions based on mass. So should be able to do both.
So you mean with the number density and the mass spectrometer data, we can actually get the total mass density, right?
Yeah.
Okay.
And I guess I'll just add on that note, you know, I'm not an instrument person. My understanding is that there can, you know, sometimes be calibration difficulties with measuring neutrals. But one of the things we'll be able to do, although we won't have an accelerometer, with GPS, we will be able to you know, carry out this precise orbit determination like we saw with, like we used with the ISAT-2 satellite. So we'll be able to also cross-compare direct measurements of neutral density along with this precise orbit determination and densities derived from there. So that will also help with cross-calibration.
Okay. More questions? Yeah, I'm curious, what's the planned mission period for GDC and after this launch?
So I think, off the top of my head, I think it's planned to be a 3-year mission with enough propulsion to be able to extend the mission by about 2 years after that.
Okay, I see. Other people got questions? I still have questions for mine, but again, I don't want to abuse my privilege as a host too much. So please. Okay, Wenbin, please.
Yeah, you did a 2-week study or validation study of the model, which is a solar minimum 2018, right? So F107 is below 70.
Yeah.
At that time, the F107 is not good indicator of solar UV as Stan and Lin found. So are you planning to do the same validation for a little bit higher solar activity levels as we move in towards solar maximum?
Yeah, definitely. We want to expand this to different solar activity levels, as well as different geomagnetic activity levels. We also would, you know, like I mentioned before, Josh Pettit is working on including FISM, both daily and flare spectra, working on including that capability with our ITM models. So, you know, with that, hopefully we can, you know, look at the potential influence of using F10.7 as compared to a more realistic solar spectrum.
Yeah, thank you.
Okay, thank you, Wenbin. We got another question in the chat from Thomas Berger. Is NOAA involved in providing real-time data downlinking from GDC? To my knowledge, NEN cannot provide real-time downlinking.
Let's see. So that's a good question. We are planning to make this data available, I think, primarily using commercial networks, is my understanding. And we're working with NOAA to make sure that they'll be able to receive whatever data we provide. Does that answer your question?
Okay, Lisa, thanks. Okay, more question? Yeah, I have one last question. Sorry. So yeah, so as we know, the different models getting updated by the developers. For example, you mentioned the CMIT, but now we are moving on to the major model based on Gamera and TiDCM. So what's the strategy from CCMC perspective to get along with the dynamically updates of the different models?
Yeah, so we're moving to a new model for doing that. We used to just sort of take the models from the model developers, install them on our systems. What we're doing now is we have AWS, Amazon Web Services environment that we're trying to mirror as much as possible what the internal CCMC systems are like, so that we can give access to the model developers on the AWS system. So that way we'll have the shared environment where model developers can install their models, can work with us on developing scripts for running the models. And then once that is ready, it can be transferred over to CCMC servers.
I see. Yeah. Hope that will help a lot for us. For example, from the Mage team to get our product on board and get it used by the community. Yeah. Okay.
And I guess I'll just add, especially for Mage and other models, even WAC and X, some of these really big models, we're also using Pleiades. And so, we don't have exactly we don't have a shared directory in that case, but we can have a shared environment in the sense that both the model developers and CCMC can both be on Pleiades, looking at the same model, looking at the same directories and working in there.
I see. Yeah, I think I just started getting involved in that. But yeah, look forward to the future progress. Just one last time. Do people still have questions for Katie?
Yeah,
Lean. Okay. Yeah.
I have a real quick question on this slide. It says, Katie, you said TEC model validation. So this is not just the model that is mentioned, like TIG from TIGCM, CTPE, and then you validate the TEC from this model, or it's actually TEC model?
Sorry, yes. Validating the TEC from our models, like
from the models. Okay. All right,
Yeah.
thanks.
Okay, thank you, Lean. Okay, I think we have got a very good discussion and a very nice talk by Katie. Let's thank the speaker. Please unmute and applause. Okay, also, yeah, thank you everyone for staying. So we will see you next week, another colloquium. Thank you, Katie.
Thank you.